which should be equal to 0. If it's equal to 0, then my delta U is equal to 0, which means I am at constant internal energy. So, and I just said, which is the work that gives you 0? Expansion against vacuum. So that's exactly what we did, yeah? You're all as good as Joule. Or better, huh? So there's a throttle over here, so this is vacuum, yeah? Pressure equals 0 in this particular chamber. And there's gas inside this yellow chamber. And then you just open this throttle, all of a sudden, all the gas enters over there. Its pressure is 0, it's vacuum. Yeah. Well, of course, in reality, it can never be 0, but it's 0 for all our considerations. The gas expands, work done is 0. So delta U is equal to 0, and then I put that back into the expression that we had, that du is 0, and what I get is del U by del Vt, which in fact is also written as pi t. Okay, so I get that back. And I say, okay, so if I remember everything correctly, pi t is equal to minus of Cv dt by dV. That's what I think I really get, yeah, at constant U. The thing inside the bracket is V and the one outside is U. Huh? So don't confuse between those two. Again, for an ideal gas, this was 0, right? Somebody just pointed out. For the real gas, it must have some value. Maybe I could put the equation of state of the van der Waals equation of state and try to get some value. Perhaps I'll get something. But whatever Joule observed was essentially 0. He could not observe any change in temperature when the volume was changed. Okay. Since it was 0, he concluded that pi t is always 0. But it was 0 because it's a very small value, this change in temperature with change in volume. Okay, it's a very small value which is now determined for different gases when you have much better instruments today. But at that time he said no, it's 0. So it only gases internal energies only depend on the temperature. But he did also mention, I think, or perhaps I cannot detect it.
So why is it pi t there? Have you kept the temperature constant?
There.
Why is it pi t?
It's 3.
Then the experiment you haven't kept that.
No. This is change in internal energy with respect to the change in volume at constant temperature. You're right, in the experiment we have not kept the temperature constant, but when we learn a bit more about these manipulations that we do, you'll realize that all of these could be related to some other quantities. Okay. For example, if you know the Euler's rule, yeah? So you could take 3 quantities, so A, B, C or X, Y, Z, del X by del Y, Z constant times, so X, Y, Y, Z, del Y by del Z, X constant. So go in a cyclic manner, and that is equal to -1, I think. Yeah. So if I take one of those on the other side, so let's say del X by del Y, Z holding Z constant, that is related to del Y by del Z. So then you get a confusion over there that no, I'm changing Z now, but here I'm holding it constant. Yeah. So these manipulations can relate a lot of quantities. That's not a problem. Yes? This is in general true. But if you calculate for ideal gases dt by dv at constant u, you get it 0, yeah? Or del u by del v at constant t, you get it 0. That's a very simple calculation which you could do, right? For ideal gases, yes, it comes out to be 0. Sorry? Yeah, use the equation of state and you get to be 0. Huh? For real gases, depends on the equation of state what the value would be, but the value is very small. Okay. So, that's about internal energy which I wanted to tell you. Then there's another quantity called enthalpy. And why we use enthalpy is because most of our day-to-day activities are at constant pressure rather than being at constant volume. So you define this quantity where H is equal to U plus PV. Okay. And there are a lot more manipulations that I have done which also shows that a change delta H is nothing but the heat exchanged at constant pressure. So it's there in the handouts, it's a small derivation. Okay. Now, if I go back to the same thing, then I write a change in dH would be equal to the way we had done it for internal energy at constant pressure times dt plus del H by del T at constant temperature times dP. And analogously, you can tell me what this fellow should be called. Cp. Right. What is this fellow? We have to worry about it. And again, if I think about what kind of an experiment that I have to do, then I would say, okay, somehow I need to get this dH equal to 0. Yes? What's that dH? How do I get dH equal to 0? That's pretty tough to think, actually. Well, if I go back, I say, okay, delta H is equal to delta U plus delta PV. And believe me, it's not so easy to think the entire experiment, but maybe I could guide you up to a certain point over here. So delta U plus delta PV, so which means P delta V plus V delta P. Okay, so somehow I need this entire thing to go to 0, right? So delta U is nothing but Q plus W, and that W is nothing but minus of P dV plus of P dV plus of V dP, right? Something of that sort. Oh, I just changed from delta to D, sorry. But I hope you understand. Huh? Okay. So, in that case, I should also perhaps write dq. Now, the thing is that, how do I get all of this equal to 0? Okay, fine, these two things will get cancelled. Yeah. If I put dq equals 0, then somehow I need this fellow also to go to 0. Yeah. Constant pressure. No, I won't be able to get actually. It's not so easy to devise this by just using this plain line of thought. So let me just tell you the experiment itself. So the experiment that Joule Thomson, so this is the Joule Thomson experiment, is that they took this box and so they have some gas on one side of the box. Okay. So the entire gas is on the right side. So I'll draw like this. I have a piston over here. The entire gas is somewhere over here. And let me say it's P2, V2, P2, defined by this. And I take this piston. Okay, there's one important thing over here. It's not just a piston, it's a porous piston. So, what you want is